Hey, what's going on, guys? Games here. I've been deobfuscating world's smallest chess program written in JavaScript by Oscar Toledo within the video series of up to 6 videos, and this is the point. This is the bonus part I've been promising you to make, like an overall summary of the entire work that has been done. But for those of you who didn't see that series or not interested in the details of the deobfuscation process on its own, I would like first to give an idea what kind of chess program are we talking about and showcase how the source code of the obfuscated version looks like, that one, the smallest, and how the deobfuscated source code looks like. And then we'll go through the code, trying to highlight the most important things of how this engine actually works, which is going to be really exciting. So if we go to the chess program section of nanochess.org, which is the site by Oscar Toledo G, who is the author of this world's smallest engine in JavaScript I'm talking about. It's also written world's smallest chess engines in C, in Java, and that's probably pretty it. And also in x86 assembly, even the bootable version of chess, which is very exciting, and probably will cover that in one video one day. But at the moment, today we're going to be looking at this one. So Toledo JavaScript chess, and this was a winning entry for this is a winning entry for international obfuscated C contest, but that's another version. So this one is actually for JS1K contest, I believe, and the eventual version is here, and we can click it and we can play it in the browser, and we have a look at the source code. Then here is the entire source code. So it's quite pretty impressive, right? So how this piece of code actually result in playing chess? Well, this is the proof of concept that it really does. Oh, I'm sorry. And it even plays random moves every time we start a new game. So it has kind of randomized evaluation. Well, as far as it's randomized, it's not always that. Okay, so now it's different move. So yeah, hope that's clear. Okay, and here I have exactly the same program, but a little bit with the bells and whistles. I've added some debugging information, and the source code for this one is available right over in here. So I've added the commentaries everywhere I could, basically, and if you have a look at the variables, so from now on the variables have the meaningful names, which gives it which makes it much easier to understand of how the entire game logic actually works. Okay, and also I've added some code for debugging. So this squares array allows to map the board square, and this is to human readable notation, which allows us to output the best move in the console. And also this print board function comes very handy when it comes to inspecting how the move generator works. So it allows us to print the board in the console and see how the moves like been make, like all the pawns and then the knights in a certain position and so on. So depending on the position, it generates those pseudo-legal moves for every given piece. And then if the king has been captured, it just returns the maiden score, and that branch is getting pruned. Okay, so but let's just go step by step, basically. And well, the very first thing to consider, I just want to show you that this game is exactly the same as the one we just had a look at. It behaves absolutely the same, but with this like additional debugging information. So we're printing the board and specifying the best move that was made by the engine. Okay, so another proof that this is actually the program that we have here in the source code. So you see, like, we have the squares. So I just want to show you that the squares are available as well. So just this is really the code, and yeah, this is really the output. It's not just a different engine rendered with a simple graphics, not at all. It's exactly the same engine. Just all the variables has been given like meaningful names. If you're interested in watching the process of how did I do this, actually, I highly recommend to have a look at Deobfuscating World's Smallest Chess Program in JavaScript video series. And this would give you an idea, like basing on assumptions and trial and error method, and then the verification of those assumptions. I eventually converted every single letter from the original source code to eventually come up with this sort of a version, just basing on the chess knowledge, on the chess programming knowledge that I have as a chess engine developer myself. Okay, so well, we probably should start with piece encoding and board representation, which are available here. But actually, let's have a look how exactly we know that this is the case, that these are the exact board representation and the exact piece encoding. So I can skip the code that I've written for debugging purposes on my own. So nothing really interesting here. So this code is the code that I've added. So it's not the original work, so we're not interested in that. It just allows to print the board to the console, and this is the output of that code, the print board function. Yeah, by the way, we can now say print board, and we just print the current board state. That's pretty it. Nothing special. And this array just allows to map like the board square to the move notation, which results in printing the best move coordinates, like the best source, best target square being converted to this notation. So nothing really special here. Okay, now when it comes to the engine on its own, one of the interesting things in regards to obfuscation itself is that all the global variables that has been used by the engine, and please know that these variables are really global because there is no var keyword here, and even though they have been created within the for loop, it might seem that they can have the scope only within this for loop, but this is not true because of no var keyword argument here. It actually is being declared globally, and two of the most essential and most interesting variables we need to have a look at is the board and the move offset. So the first contains the board and the board array, the board representation with the pieces. It also has some additional data, which I'm not sure whether that's, well, it doesn't seem to be doing anything. So it seems like a side effect of this highly obfuscated initialization routine. And it seems like, again, one little note, guys. So when I say it seems like, that really means what it means, because after deobfuscating the source code, I've realized why Oscar Toledo, the author of this engine, actually allowed me doing this, even though he is selling a book explaining how this source code works. So I was thinking, like, if I deobfuscate the code, then it just was the reason to sell the book if the information would be available for free. But he wasn't concerned about this, and I was wondering why is that so. But then I realized that even though we have this meaningful variable names, this doesn't understand that this doesn't mean that we fully understand how the entire program works. So I think that the question that I can answer, and the question I'm answering within this entire video, is what is going on. So what is happening? So the question is what. But I believe that Oscar Toledo's book should answer the question how. So how exactly is that happening? So whenever I say it seems, or I assume, or might be, or possibly, this can be revealed like 100% sure how exactly that works if you buy his book, and there would be links in the description below. I'm tempted to read that on my own as well, but actually I didn't give up the intent to figure out this on my own. But at this point, I'm pretty satisfied with this kind of deepness, this understandings of how deep it is. So it's fairly enough for me at the moment. So this sort of a for loop does all the initialization we needed. So again, one more thing. So before we go to the board and move offset, so we have another few variables like we're interested in. So best source and the best target are so here they serve some initialization purposes, but later on they would be absolutely key variables because they would be storing the best move being associated with the best score returned by the search function, and that would be the move that is actually made on board. And also they handle the user input as well. So it's kind of like a multi-purposes variables here. Move offsets array index is an index to set the move arrays to get the certain the pointer to the element within the array where the move offsets for a current given piece type takes place. Okay, move set array index. Oh my god, I already forgot what I did here. Move offsets data index. Okay. Okay, yes, yeah, it's just it comes more clear when it comes to the code. I'm sorry, just so many variables, and I actually didn't make this entire recap. I've been replacing them by the time of the deobfuscation series. So yeah, just let's go step by step. So the first one I want to show you is the board, and if we just type the board here in the console, then we see this kind of like entire board representation, but it's not really good to see this in this way. So we have the 7, which stands for offboard squares. Okay, then we have this starting from rook, knight, bishop, queen, king, etc. And then we go for white pieces. So these lines represent the white pieces, and I made a shortcuts for this, so the piece encoding is available here as well as the board representation. And based on this, I've created this function to actually print the board to the console. So it uses it uses the array-based. So the board is represented as the one-dimensional array. So we have the board known as 10 by 12 elements. So this extra offsets needed for detecting off board. So in order to avoid, say, knight jumping to and not to the next rank, and yeah, so that's the purpose. So these 7s just don't allow the pieces jumping from one rank to another if it's not intended. So that's the case. It's one of the oldest and one of the most essential, one of the most basic ways of how one can represent a chessboard. Okay, one of the easiest, one of the simplest ways. Another alternative might be a hexadecimal 88 system, which is quite different but also works quite interestingly. Okay, so and another one is the move offsets. This one. So if we have a look at the move offsets, so let's have a look at the move offsets, and here we go. So for some reason piece codes are initialized here as well. This might be a side effect, I'm not sure, but what is actually used here are the move offsets, let's say like for rook potentially, yeah. So also like for, say here it's for white pawn, I know this for sure. So like pawn captures diagonally minus 11 minus 9 minus, because index 0 stands here. This is index 21. How I know this? I can just inspect the element, and here we have this 21, which serves as an index. So 29 here. So we can capture diagonally, minus 11, minus 9, minus 10 is just one step forward because we have our board width being equal to 10, because we have this 10 elements by 12 elements, so only 8 visible, but there are 2 more invisible, as has been shown on the board. The board layout is here, so it's 10 elements here, okay? What else? So minus 10 pawn goes 1 square up, minus 20 double pawn push. That's pretty it. And we have the offsets for all the rest of the pieces. And these big numbers, you might be wondering what are these big numbers are standing for. So they stand for so it gets, we'll see exactly how this mechanism works, but just to give you an idea, so let's take, say, this one. 66, right? So it points to 39, and 39 is the index. So we go here. Here we have the exact offsets for a piece type that lands here on the, somewhere at this index, right? So we'll see how this works. So this is the next thing to consider, just right in the moment. Okay, so all this initial for loop does is, so the main thing is just to initialize this board array, so to set up the pieces on board and move offsets as well to literally initialize like the game, the rules of the game, so how exactly pieces are allowed to move. That's pretty it. Also some additional data, but again, like I'm not crystal clear on how the entire thing works. So again, like you can buy a book by Oscar and find more guardians there and just answer literally every question, I believe. So the main function and the only function that is used here, well, actually there are two. So the second one is just simply renders the board. So render the board is quite pretty simple. It's nothing really to have a look at here, except this is a masterpiece of obfuscating, rendering the entire the set of HTML element div elements. No, not the divs. These are table header elements. Yeah, table header, and the board is a table, so we have table headers as the columns, and this is all done in one line, and this is a real masterpiece. So it's, I'm not diving into how exactly it works because I didn't figure that out on my own, but it's clear enough to say what it is doing, not how. Okay, so just the draw board function literally updates what we currently see on our screen right over in here. So I hope it's clear. Okay. What else? And the main engine function is this one, search. So let's start with the parameters that the search takes recursively. So site to move is changed every time when the search function is called recursively to generate moves for whites and for blacks respectively. Search ply is an internal variable which is used. It's hard to say. Well, it's definitely used to determine the shortest distance to the mate, but part of that, it seems like it's being used for some helper functions as well, which I didn't understand completely, hence not going to be talking about that. Search depth is how deep the engine is going to be searching, and this one, which I call the score difference, again, like I'm not really 100% sure how exactly this one works, but my assumption that this is something to distinguish between the maiden and non-maiden scores potentially. So again, like it's an internal it's only internally used argument. So when the search function is called explicitly, it's not being used at all. So if you just see how the search function works, so let's try like currently like this. Okay, so just to give you all the occurrences of the search function. So the first one, so so here you see like we have only two arguments, only site to move and the ply, and we don't even have the search depth. Again, I can't be 100% sure about this, but bear in mind the fact that this is the king capture engine, I think, and we need to make sure that the score is greater than and if I'm not mistaken, this is the constant for a maiden score. So I might assume that here the call of the search is needed to determine to answer the question whether the king has been captured or not, and based on that we need to actually need to prune the branch that is occurring after the king has been captured. So I hope that's pretty self-explanatory, so to avoid making illegal moves. But this is done on the fly, and not really as the side effect, but yeah, this is done on the fly, and also somehow the return value of this, well, actually it returns either true or false because we have the greater sign here. So I guess I would interpret this if it's not mated, so, or if the king is not being captured, because if we have a king capture which occurs here, in this case we just return the maiden score. So I assume that this means if we're not mated, in this and the search depth is not equal to 0, so it's something available like 1, 2, 3, etc., then we know that king is in check. Well, I'm sorry, guys. I said it wrong. So if the king has been captured, not if the king has been captured, obviously. So if we exceed the mating score, right? So here we do return this. So if king is captured, in this case, we know that he is in check, and we're not going to be generating moves anymore. I'm sorry, just I said it wrong. Okay. So what else? Score is the score for a current given position. So we make a move, we need to score the position. It's not really that clear how exactly the scoring is happening, because naturally it's done like getting the piece weights and using the p-score table to give positional scores, to give an engine an idea where to develop its pieces. But in this particular implementation, I can't reveal neither of those. And the way how the score is calculated in this engine is really strange, to say at least. And I also didn't find the piece weights. So potentially might be the piece code serve as the piece weights. This might be the case. By the way, let's have a look. Is this really 5, 3? No, the queen is miserable. Well, I don't know. It's hard to say. So I'm not going to be talking about what I'm not sure 100%. But anyway, so let's get back to the search occurrences. So here is the first one. Here is the recursive call. So yeah, by the way, I can say that this is the recursive NegaMax call. So this engine uses NegaMax framework, but it's a brute force search, so we don't have the alphabet upfront in here. And no move ordering, and no need to get bothered about stuff like that. All right. So the second one is when. So this one is used when engine is analyzing. So it's like makes move for white, makes move for black, then makes move for white again, and repeats this until the search depth has been exhausted. Meanwhile, increasing the. Oh my god, search ply. Yeah, so search ply is getting increased because every time we make a move, the ply increases, and this ply is later used to find the shortest distance to the mate, which occurs here, I believe. So we have this mysterious 78 constant minus search ply. So I guess that the score for the shortest distance to mate happens here when the mating score variable being initialized. So it involves the search ply to alter its. So it's a constant. It should be constant value, but it uses a search ply, and that's pretty. So, but if I'm not mistaken, it gets something like 10 thousandths, and yeah. So well, I might be wrong. That we can really check this here, but I don't really want to let this video to last forever, so we just keep this for now. Okay. So this is the next occurrence of the search. Then I'm not sure exactly how this works, but what I know for sure, if we want to increase the search depth, it should be done here. So by the way, we can give an extra commentary here. So we say change 3 to the desired search depth in first search call. Okay, so just a hint on how to make it searching deeper. Okay, and again, like I'm not sure, but this again seems like test for whether the king has been captured or not, but I'm not sure. Is this the duplication to this one, which was done here or not? So this is a bit of a mystery for me, so I can't say more about it. Okay, and also it has been called here. So literally every time. So this is the initial invocation of the search. So every time a user makes a move on the chessboard, so this happens within the onClick method, or onClick callback. So as soon as user kind of clicks on a piece, moves the piece, it gives this sort of an idea. So just the search farts and starts searching. It's a bit unclear what the heck is going on with this parameters, because we just given we always ask to search for black and only one ply depth, but again, like, this somehow gets replaced by this one later on, so I can't sure how exactly this is working. Probably, by the way, hold on guys, I'm just wondering, is this is it low into, no, it also has the move validation, believe it or not, you see. So yeah, it also has the move validation. So I didn't know this, so this is another interesting option, so just didn't. So yeah, probably that is the reason, maybe that is the reason. So yeah, it's I don't know, but yeah, a very cool feature that it does have a move validation, which is absolutely fascinating. Okay, so this is where the search has been called. Okay, so yeah, the variable names are self-explanatory in terms of what they're doing. And now, well, usually this minimalist type of engines, like this one, like Micromax by Harmgerd Müller, like those, I've been trying to handcraft, which result in bigger size and didn't work that nicely as this two most minimalist, most small from the code size perspective engines. So this type of engines usually involves 3 stages within the move generation, and it's even known as the three nested loop move generator. So the first loop should go over the board squares to pick up those pieces that belong to the side to move. The second loop should be over the move offsets to figure out what directions every single given piece is intended to go. And then for slider pieces, we need to, within the current given move offset, we need to kind of loop over the attack ray. So for slider pieces, like for bishops, queens, and rooks, this is what should happen. But Oscar Toledo is so smart that somehow he has reduced this. So somehow he has combined the loop over move offsets and over the directions, and into the kind of like squares along the attack ray into one single loop. So eventually we have 2 major loops. So the first one loops over the board squares, and it's clearly seen here. So source square, sorry guys. So the source square is the variable that holds the current board square, and picks a piece there. So picks the piece of the side to move we're interested in. And then the second loop here, we already loop over the board target squares, but this also assumes that sometimes, not sometimes, this assumes that for slider pieces we do loop over the direction, and for leaper pieces we don't. And how exactly this is done, it's a bit of a mystery for me as well. I can figure out how a few things work here, which I'll cover, but the rest of them is still not really that clear. Okay, so what else? Yeah, so init move piece to whatever target square. Yeah, so 2 interesting types of the variables. So moved piece and the source piece. And these 2 would have been the same in case if we didn't have pawn promotion. But as far as we do have a pawn promotion, so if we use the source piece, which is pawn, right, but it gets promoted, it turns into queen, and source piece turns into a queen. So we take it back, we would have a queen in place of pawn. So in order to avoid this, we keep a separate variable which is called moved piece, and this moved piece would always be keeping that sort of a pawn. Okay. So moved piece is initialized the following way. So we take whatever available at the board target square, and meanwhile on the fly we do initialize the target square being equal to source square, which allows us to later on add the offsets to the target square to get the actual target square based on the current given move offset, plus the increment within the direction array, the attack direction array, if needed for slider pieces. Then the piece type is being extracted in an interesting way. So I've been explaining this in one of the videos on the obfuscation series. It's also not going to be telling this again. Okay, now the offsets number. So here is a little hint what it means. So we have 8 directions for knights, queens, and kings, and only 4 directions for pawns, rooks, and bishops. So why 4 directions for pawns? 1 step ahead, 2 step ahead, and 2 diagonal captures. That's why we have this 4 directions exactly. Okay, so this is a helper variable that gets initialized. It also needs to get initialized. Okay, now move offset index that I had stuck a little bit at the very beginning. So what this guy does, we would later index our move offsets array by this move offsets index. So this allows us to know, based on the moved piece and based on the piece type. This is the case for white pawn because it's the only piece that is for all the pieces but pawns, it doesn't matter whether they go in forwards or backwards because they have the mirror directions, but only the white pawns and black pawns have different directions. So in this implementation, for some reason, somehow black pawns, as far as they go in like in the plausible direction, they're not touched and they're treated to be as irregular pieces, while the white pawns is an exception, has this Turner operator, and we do distinguish between the white pawns, which results in this 49, and if we have a look at the move offsets indexed by 49, so we have move offsets indexed by 49, then we have it's just better say just move off. It's better to say starting from 49 move offsets. Starting from 49, we have this that I've been mentioned already. This move offsets for white pawn. Here are the 4 offsets for white pawn. So diagonally capturing, white 1 step forwards, and double pawn push. Okay, and for all the rest pieces, we do calculate them in a bit different way. This also has been covered within the Deobfuscation series, so if you're interested about the details, you can have a look at this as well. What else? So then we start the loop over the target square, so where exactly the certain piece can land, and then the initial square occupied by the square by the piece and the target square would be what the move consists of, like e2, e4. So from where and to where is that going? Now here we have a very important part. So capture piece is the variable that stores whatever piece being available at the target square. So let's say we capture a piece. So how do we know that? How do we restore position when we take the move back during the analysis? We need to take that piece from somewhere, and this somewhere is exactly this capture piece variable. So that's the variable where we're storing whatever has been on the target square before we put a source piece there, and this happens here within the make move. Okay, and by the meantime, so in order to get what exactly would it be at the target square, so here on the fly we do increment the target square by a current given offset based on the piece type, and in case for leaper pieces it's just done once. For pawns, we also obviously don't capture diagonally if there is an empty square, which is defined here. So if we didn't capture anything, we just don't get into this loop and we just skip further on. So it's kind of one of the most mysterious parts of the code if we don't take into account the search algorithm, like the scoring and this mate detection, stalemate detection, things like that, which is a bit of a mystery for me as well. So yeah, so we do so here is the core increment of the core part where the target square gets incremented by whatever we have the move offset. So let's say for pawn we have this value like -10, and we do have the source square equals to say this one E2, which is 85, so 85 minus 10 would be 75, so 85, 75, this would be the double pawn push for a pawn. 85, 65 would be this was single pawn push, and 85, 85, 65 would be the double pawn push for for pawn, and this would result in a move E2 goes to E4. Okay, so, and the same for the rest of pieces. And now you might be wondering how to prevent leaper pieces from sliding along the move offset, and this is done, well, it seems like it's done exactly the same like it's done in the NegaMax engine by Harm-Gert Müller by faking a capture. Well, again, like I'm not sure that, sorry guys, I'm not sure that this is done. So I just see that this loop over potentially this attack array as well is done only in the case if we don't have a captured piece. However, it's not clear how exactly, well, or probably we have a restriction for leaper pieces somewhere here as well. So yeah, maybe yeah, I was too hurry to say that. So maybe it's not done while faking a capture like it's done in NegaMax. Maybe it's different. So I don't know how that's done. I'm sorry, just I don't really know how exactly. So it still needs to be figured out later on. Okay, what else? Yeah, so we do continue our loop, and basically in this piece of code, as well as in this piece of code, we have a really huge amount of rules, literally all the rules of chess. So this kind of, so we just don't get in here. Let's say if we want to capture with pawns diagonally and there is no piece, or if we want to move a piece forwards 1 on 2 square and there is a piece, and all the set of this nitty-gritty rules is actually being handled in this and this part of code. I'm not exactly how exactly where in particular. Well, this and also pawn promotions is handled. By the way, is this about the pawn promotion? This might be. Yeah, this might be. Well, I don't want to be guessing because yeah, it just doesn't make any sense. So let's move further on, and we're coming to one of the most interesting and exciting parts. So the most interesting and the most exciting part starts here. So I just want to show you one little trick, then you can try on your own as well if you're interested. So if we just okay, so it was a bad idea, so let me just manually to comment out all of this part. And yeah, so if we just go update, go to the console and ask the engine to search, let's say, or it doesn't matter which site. Okay, and yeah, and one more thing to consider. Yeah, we also want to say print the board. Yeah, to get the maximum effect here, and alert to break the execution. And also here we say print board. This is my favorite part, and alert as well. So we'll see how the move generator works, and this is gonna be really exciting. So let's just update, and now we're generating all the pseudo-legal moves for white pieces. So I'm gonna be just hitting enter, and here you just see how the pieces are moving. So while the move's being generated, so this is like the most exciting part for me personally, guys. I don't know how about you, but for me personally, this is the most exciting part ever. And let's say we want to generate the moves for the opposite piece side. We can do it by this, like this. You might be wondering that I've said that 8 belongs to white and black belongs to 0, and why this works on the country. Well, that's because of this piece of code. So we just comment out this one as well, then this should be in theory so now this should be for white pieces. No, it's still for black. Okay. Probably, maybe not there. Yeah, I don't remember already. Yeah. Yeah, it doesn't help. Okay, it doesn't matter really that much. I've been proven that 8 stands for whites along the series, so you can check it out there. Okay, and also, yeah, so that has been proven in the series on its own. Just that was a bit too complicated. I don't remember it already, so you can just have a look at the series for more detailed explanations. Just can't keep too many things in my head at the same time. But yeah, let's just have a look how the moves are being generated for the opposite side. So this is how it's happening, and in whatever position we would be having some different move offsets. So just to give you an idea, so let's remove the pawn on e4 and put it on, let's say, let's play e4 e5 and then try to generate moves for whites, right? So I want to inspect. Well, by the way, hold on a sec. Can I do with this sort of a index of hold on a sec, guys, just want to check one little thing. So if I say squares index of, and let's say e2, yeah, it gives e85. Okay, so now I can even say like board index of e2 is equal to well, let's say code for pawn is 9. Okay, so it's equal to 0, and e4 is equal to 9, and let's just print the board. We won't see this on the left part, but here we see we just moved the pawn manually by hands, literally. And now let's say index of e5, it would be equal to 1, which stands for black pawn, and e7 is going to be equal to 0. And if you print the board again, here we have this position e4 e5. And now if we do search all the moves for white pieces, so obviously it will start moving not only like it was in the initial, but also the queen moves are getting available, so like the king moves. So literally all the pseudo-legal moves has been traversed, and that's how it works. So I don't know about you guys, but for me personally, this is one of the most exciting part in regards to chess engines in general. So I'm not really interested in plain strength, but for me personally, chess engine would always remain a move generator. Okay, so let's restore our code back so it's still playable, and then we move on. Okay, and also, yeah, don't forget this one, save. So now it should still be capable of, oh my god, oh, this wasn't clever. Okay, sorry. Yeah, get rid of this lines, of this one. Okay, and now it should be, yeah, so hopefully it's still working. Hopefully it didn't break anything. Yeah, seems like it's okay. Perfect. All right, so yeah, we're done with the move generator, and yeah, literally it's almost everything that I can say about this engine. So make move, then recursive call of itself to analyze the moves for different sides of move until this value of the fixed search depth is getting exhausted. I'm not sure how exactly the escape of the recursion is happening here, so it's somewhere in the code, but yeah, it's really hard for me to say how exactly. So we do restore the move after, and here is the brute force NegaMax search algorithm, and the only part that I can understand here is this one. So we have the score is greater than the best score, then oh my god, no, the best, yeah, then yeah, then the best score gets equal to score. So this is another hack. So we do this on the fly, and then yeah, and another interesting thing that I am am capable of understanding. So here, if everything is the case, yeah, we have this best source variable being associated with the source square, while the best target being associated with the target square. And this allows us to do what I'm printing here. So printing the best move, like just converting this to user-friendly format using this array to map the board index to the human readable notation. So we have the best source and the best target square being printed on the screen when the engine outputs the best move. So this is how it goes. A7, A5, best move. So yeah, just a proof of the fact that this. So the idea is to associate the best score that has been returned from the search with the best move. Okay, to make that move on a chessboard. But how we do this? So we have these global variables of the best source and the best target being initialized at the very beginning of the source file, here and here. Okay, and once we are done, well, actually, I believe this they are getting incrementally updated until the best move still gets fine, and then they just keep there. They just remain at the best ever values they had. So yeah, that's probably the case. And then we just use them, and then for some reason we do reset the best score being best source being equal back to the back target. But bear in mind the fact that they are also being used to represent the human. Sorry, what's this next? What this new line? We don't need this currently. But as far as this best source and best target are also used to keep users best source and best, literally like where the user has moved. So first it was undefined and offboard, then it's offboard and E2, and then finally when I click on E4 it gets E2 and E4. So we use exactly the same variables, and then these exactly the same variables start holding this C7, C5. That's pretty. And again, like, yeah, one more thing that I can show you guys, and this is this line, which allows us to randomize the play. So if we just get rid of this, so this would be the one last hack I'm going to be demonstrating in this video, and we're done. So we just get rid of this one and try to play. What the heck is? Oh, that's because, yeah, like this. Yeah. Save, date, what, unexpected if, oh, yeah, it should be like this, I believe. Okay, so now we would always be playing exactly the same game no matter how many times I repeat. So again, same game, and again, the same game. By the way, this gives us an idea of the true evaluation that has been used, and yeah, it doesn't really seem to be using any p-squared tables, because the p-squared tables won't give this most. But yeah, this small amount of code doesn't allow for, well, having a p-squared table would be very expensive. So it's not the case. So like we're always playing the same game. However, if we just restore things back, and so the way how this works, so we are in the territory where we found a better move, where we've just found a better move. But also we kind of like randomize our evaluation. I mean, like, not randomizing the evaluation and so on, but we do go for associating the next best square, the next best move with the next best score with the best move, only in the case if this random number would be less than this kind of constant value. So we randomize not the moves, not the evaluations, but we randomize the fact of whether we should update the best move or not. So that's how it works. That's something I couldn't figure out in the previous parts during the deobfuscation itself, but that's what I can clearly see now. And yeah, eventually here is the return that fires when we do loop over all of the moves. And yeah, that's kind of pretty it. Okay, so I can't say anything more about how this works, only what works, just a very brief explanation. So despite the fact that we have all the meaningful all the meaningful variable names for our variables, and it's now possible, if one would be patient and goes debugging every single expression step by step, trying to figure out what exactly it means, how it works. In that case, you will definitely come up with an understanding of how this works. But for those lazy, and I think it's really a good idea to buy a book, because it's I don't remember the price. It was something around $10 or something like that. It was a really miserable price as opposed to this huge titanic amount of work that being done to develop this actually. And the book, I know that the book also doesn't only contain the commanded source code and the explanation of how it works, but material on chess programming in general, so how to write a chess engine. So that might be even more interesting from that perspective. So I highly recommend you to buy one. Okay, and I think that we're done within this video. So thanks for watching, and yeah, so this is kind of it. This is it, guys. So thanks for watching. Until next time, and take care.